Hello everyone, welcome back to this second lecture in week 10 of the Blue Planet. Today's lecture is on currents and circulation, and we'll begin exploring ocean circulation, focusing on wind-driven circulation in the surface ocean. Our learning objectives for this lecture are how winds drive circulation of the surface ocean, how convergence of water flow results in downwelling and divergence in upwelling, how planetary vorticity deflects current flows to produce Ekman transport normal to the current direction, how winds drive upwelling or downwelling along coasts, and how the large ocean gyres are formed in the ocean basins with warm western boundary currents and cool eastern boundary currents, plus much more. So many maps of ocean currents depict the circulation like this. On this particular map, we see warm currents with red arrows and cool currents with green arrows. And you'll notice that they show the large ocean gyres, these great big circulating currents in the major ocean basins, like here in the Pacific, circulating in this direction and then in the opposite direction in the Northern Hemisphere. The simplicity of these diagrams ignores the great complexity of the actual currents. We'll just take a minute, and I suggest you take a little bit longer to look at this animation of the surface ocean currents produced by NASA called the Perpetual Ocean video. So you'll notice the complexity of the ocean currents. Here we have the Gulf Stream running up the east coast of North America into the North Atlantic. You'll notice all of these eddies spinning around along the equator. You'll have directed flow, the Agulhas current with very big eddies here called the Agulhas rings. Here we are moving up into the northern Indian Ocean. Across the Bay of Bengal here, it's the coast of Indonesia. Here we have the Kuroshio current going up the east coast of Japan into the northern Pacific. Notice how complex all of this flow is here. And interestingly, when you come over to the eastern side of the basin, it's complex, but the flows aren't as strong. On the eastern side of the Pacific, here we are coming up to Antarctica, and we have a circulating current that goes right round Antarctica, the circumpolar current which runs from west to east. And here we have our neck of the woods with the East Australian current coming down, breaking up into eddies, and part of the current flowing across here, across northern part of New Zealand. But again, very complex flow. Anyway, take your time, have another look at that at your leisure. Picking up now where we left off. To understand how these currents form and why they're so dynamic, we need to understand a little bit about how wind drives circulation in the surface ocean. So winds exert a frictional drag on the ocean surface. So a wind blowing, in this case, from right to left across your screen, has a frictional drag force on the surface of the ocean that causes the water to move in the same direction where it's directly in contact with the wind. So that frictional drag is said to induce surface flow and wave propagation in the direction of the wind. Gradients in wind speed cause downwelling or upwelling of water in the ocean by generating convergent or divergent current flows. And these current flows are deflected by the Coriolis effect due to Earth's rotation. Density is also an important factor for understanding current flow in the ocean, and particularly ocean stratification. We'll come back to density in another lecture, but the important point is that less dense water floats on top of denser water and always lies above denser water. So this is depicted here, where we have low density water lying above water of a higher density. Where the low density water is thicker, it will actually form a high point in the ocean. So convergence and divergence of flows is a really important concept to understand. And I'm sure you've considered this in terms of convergence and divergence in atmospheric flow. So it's similar in the ocean. Where we have convergent flow, we have a piling up of water. So these surface layers become thicker and we get downwelling of water. So thickening of the surface layer is causing downwelling where we have convergent flow. Conversely, where we have divergent flow, where the currents are flying apart, we have thinning of the surface layer, and as a result, we have upwelling of water from depth into the surface layer of the ocean. A similar thing happens along coasts. Where we have convergent flow of water towards a coast, the low density surface layers pile up against the coast and we end up with downwelling. And again, because this low density layer is thicker, the surface of the ocean also stands higher. And the corollary, when we have divergent flow away from the coast, we have thinning of the surface layer and we have upwelling of water from deeper into effectively the space that's formed. We end up with a low point in the height of the surface ocean.